Welcome to the first episode of Robotics podcast project, a side project of Weekly Robotics. Today, with me, we have Professor Auke Ijspeert, who is a professor at EPFL at Lausanne, Switzerland, and also the head of Biorobotics Lab. Thank you for having me here in your office.
Thank you. Yeah.
So maybe we could start with how did you get into robotics?
Yes, so in fact I've always been interested and fascinated by animal locomotion. So during my PhD work I was already working on computer models, simulations of like swimming in lamprey, and primitive eel-like fish, or swimming and walking salamanders. So that was all in simulation. And I always had the dream to bring this to real life, to real robotics, and work on robotics. So the robotics came later during my career. During my studies, I had some side projects on building robots, doing like some competition of robotics, and it's only later that I started doing real robotics.
So you were always like half and half between biology and robotics, or if you were to weight this in, how would you weight this?
Yes, so I was trained first as a physicist, and then I was very fascinated by computational neuroscience. So I started by more being a computational neuroscientist, making neural network models of the circuits in the spinal cord that control locomotion. And then I realized more and more how important the interaction with the environment, the embodiment, the physics is important. And of course you can simulate it to some extent, but having real robots in interaction with real environments is really important. And that's how I started being more and more interested in robotics. I, in fact, also did a bit of robotics sideways before doing locomotion. I worked a bit, like during my studies, on making wheeled robots that had to solve some task, like some kind of, it was called a rugby competition. And I did some work on multi-robots collaborating, wheel-based robots collaborating, Kepra small robots. And I then worked into humanoid robots at USC when I worked with Professor Stefan Zahl, a colleague at USC. He had access to a wonderful humanoid robot where we studied then movements. And it's only later when I came back as a professor at EPFL that I started to focus on locomotion, which is always has been one of my main interests. And since then, in fact, we have many projects in my lab interested at the intersection between biology and robotics, mainly around all the concept of locomotion and locomotion control.
Mm-hmm. I've seen your presentation for World Minds. And there, I believe you said that there is a reflex mechanism that normally in body, it's not really handled by the brain, but it could be handled by the nervous system. Is that correct?
Yeah, well, the thing is the spinal cord circuit. So indeed, in all vertebrate animals, we of course have the main brain, the main part of the brain, which like the motor cortex, the cerebellum, all these kind of parts of the brain that are really in the head. But the spinal cord is an extension of the brain, of the nervous system, and it's a very important control center for locomotion. And people completely underestimate how important the spinal cord is, because it's really like a second brain, a very old brain, like very primitive circuits, but still very sophisticated. And it's really in the spinal cord that you find all the neural circuits necessary for locomotion. And the fact that a chicken can run without a head is because its spinal cord is functioning. It can do all the control of all the muscles. It can even have feedback loop control. And basically the spinal cord is really a beautiful control circuit that I would like to understand. And it looks like the spinal cord has changed during evolution. Like it was very important for swimming, of course, for lamprey-like swimming. And during evolution, it looks like new layers have been added on top of primitive swimming circuits to little by little allow legged locomotion with limbs and terrestrial locomotion. And I really would love to understand and use models and robots to understand this evolution of the locomotor circuits in vertebrates.
So you are hoping this will drive your research in the future, or you will be able to to use this concept in robotics?
Absolutely. So I think here there's a beautiful bidirectional interaction between robotics and neuroscience. So on one hand, robotics can benefit from inspiration from animal, not only the morphologies as we already do, but also from the control principles. And here, this concept of spinal cord circuits is a beautiful way of distributing control. And in some of our robots, we have at a low level, like in microcontrollers, we replicate the functionality of the spinal cord. And that means that high parts of the controller do not need to worry about all the motors, like for swimming to walking, but only about modulating these signals to go left, right, or to control speed. And this is exactly how in nature different parts of the brain have different responsibilities. And high part of the brain rarely worry about muscles. They only worry about high level signals. And it's really the spinal cord that has to control all the muscles, all the signals. And therefore, it's really interesting to take inspiration in robotics from the biological circuit. Now, in return, and that's maybe one of the specialty of my lab, is I love the idea of using robots as scientific tools. I think robots can be wonderful tools to very systematically implement different models of the spinal cord and very systematically test how they work. Can they replicate animal data or not? How does sensory feedback shape these locomotor patterns? And in addition to simulation tool, I think robots are really a wonderful tool to do scientific work. And that's really, many of our projects in the lab are exactly on that domain.
Speaking of using robots for science, one of the projects that I think that was in the news last year was your fossil project. I see the poster of it, I think, on the wall. So could you tell maybe our listeners what was the input that you had and how did you create this robot?
Yeah, that was for us a very cool project. So indeed, we have had many projects where we developed robots for neuroscience, like to understand lamprey, salamander, cat, or human locomotion. But thanks to that, a zoologist, John Nyakatura, he approached us to say he had seen our salamander robots, and he said, "Wow, could we work together?" Because he had access basically to a very nice fossil of an old tetrapod, it's in between amphibians and reptiles, a very old animal. And not only he had the skeleton, the fossilized skeleton of that animal, but also the footprints for the same species. So this was a very nice collaboration where, using our robotic technology, we could use it to very systematically explore what was the most likely gait of this extinct animal, this animal that doesn't exist anymore. And so the work we did is replicate the morphology of that animal as well as possible using a robot. We had a real robot and a simulated version of it. And then we use robotics technology on one hand to generate all possible gaits that could walk in these footprints of this, but then have different characteristics like different heights or different amplitude of spine movements or different use of different degrees of freedom, different joints in the body. And we also use kind of robotics tools to quantify the quality of these gaits. So for instance, we can quantify how much energy does a gait use, how well balanced is it. Clearly the animal should not want its head to move too much left and right, so the keeping balance was important. How accurate were we to walk in the footprints, and several other type of matrix quantifications. So putting all this together, we could demonstrate, first of all, that in principle this animal could have used many gaits, many possible gaits, so which is not too surprising because you have many joints, there are many ways of moving in these footprints. But if we looked at the most likely gaits, those which have the biggest scores, they were very similar to the caiman, like a reptile, like a crocodile or a caiman, which is a quite modern and agile animal, as opposed to salamanders, which are older and closer to the ground. So using our tools, we could really quantify likely gaits and make this kind of look into the past, finding that this animal was using a quite agile and athletic gait. Yeah, so for me it was a really wonderful collaborative project where another example of using a robot as a scientific tool for another field of research.
How long did this project take you?
So this project was more or less 5 years, and because it really involved a lot of work on the robotics side, of course, to make the robots, the simulations, do all the systematic tests. But also in the paper, there's an enormous study of modern animals, like where our colleagues, they had X-ray videos of many animals. They quantified the gaits, and therefore we could very systematically compare what were the prediction for this Orobatus, the fossil, compared to modern animals, to see how close or not they are. They possibly were to modern animals. Yeah.
That's quite interesting. And about robots working with animals, I think you had one project with BBC where you cooperated with them.
Yeah, that was a fun project as well. Is where at some point a producer for the BBC called us because he also had seen the salamander robot, and they wanted for this very nice documentary called Spy in the Wild. They create a whole series of different animatronics systems, so little robots or devices that look like animals and that had cameras on board. And for them, they asked us, could you make a crocodile robot for us to film real crocodiles, or at least try to. So we made the robot. They made a wonderful skin that really looks very realistic. And this was all done in a very short time period, so it was really stressful. These two were put together only in Uganda, in Africa, because both in terms of the robot and the skin took quite some time, and we had to rush. And at the end, it was quite exciting for us to have something that really looks quite a bit like a crocodile. If you look at from far away, you might be tricked to think it's a real crocodile. We didn't have as much interaction with a real animal as we hoped for, because it was a bit late in the season. The crocodiles were always a bit going away each time we were approaching with the robot. But still, the whole exercise of going into the same environments in which the crocodiles live and move, test our robots there in the same terrains and everything, was very exciting. And it's true that I would never have expected, like 10 years or 20 years ago, that one of my robots would be part of a documentary. Mm-hmm. So it was a very fun and interesting experience.
And about some other projects, I think you mentioned that your lab is also working on humanoids. Can you tell us a bit more about that?
Yeah, so one aspect of humanoid robotics we are interested in is also a bit to understand how the spinal cord of humans is implemented. Here, interestingly, we don't know much about the human spinal cord because it's really impossible to record activity of the human spinal cord while somebody moves. Technically, it's not possible. It would be dangerous. So the whole neuroanatomy and neurophysiology of the human spinal cord is really unknown. So using models can be useful to see how different types of circuits in the spinal cord interact to generate locomotion. So we have some modeling project on that. We apply them also a bit to human robots to get human robots to walk. And on top of that, we have some more high-level studies where we were interested, for instance, to see how when two humans walk together, carrying, for instance, a table or a stretcher, to see how they coordinate the gaits. Like as you probably know, as soon as you physically hold another person by hand or through a table, you tend to synchronize. Without consciously doing it, you tend to synchronize. Mm-hmm. And if you think about it, two people carrying a table together, they become like a quadruped, like a horse with two forelimbs and two hind limbs. And we found out that most pairs of humans, when they walk together, they tend to synchronize, meaning they converge to the same frequency of stepping. And they converge to a gait that would look like a pace gait in an animal. A pace gait is a gait where the two limbs on one side are lifted at the same time. Giraffes use a pace gait. A horse can be trained to do a pace gait. And some pairs of humans were more converging to the trotting gait, which is a diagonally synchronized gait where limbs in diagonal synchronize. And some pairs of people were never synchronizing. But interestingly, most people are synchronizing, and it's not conscious. It's kind of a natural thing that you do. And using our humanoid robots, we could demonstrate that, in fact, the mechanical coupling tends to have a synchronization property. So that's why just the mechanics is like any coupled oscillators. If you couple them a bit, they often tend to synchronize. And it was a bit surprising for us that our very complex human robots with very complex controllers and everything, even if you give them slightly different frequencies, if you couple them mechanically through a table, they were also converging to a synchronized gate. So it's a very generic property of coupled oscillators that you find even in complex machines. That was quite exciting for us.
Oh, that's really exciting. I never thought about that, but it makes perfect sense when you think about it. And what you would hope to achieve in the future when you look at biorobotics now, with the improvements we've seen over the years, where do you think we are going, and what would be the sort of holy grail of biorobotics?
Yeah, so there are several. So first, in terms of performance, we're approaching little by little animal agility, but we're still very far away. So of course, here everybody, and me included, we're always very impressed by what Boston Dynamics does, like with its Atlas and legged robots, and it's really beautiful. It's really pushing the state of the art. But still, it's still very far from like a cat jumping in a tree, going over branches and then jumping down several meters. Same thing for swimming. We're still very far from replicating a dolphin or a tuna swimming, or even ourselves. Our human robots are still not as good as anything we do in terms of playing tennis, like Roger Federer, or doing sports. So there's still many things where in terms of performance we're still not there at the level of locomotion skills of animals. So one dream is to push the limits into performance, so approach agility and versatility of animals. So that would be one dream. Another dream is to more and more understand this really fascinating mechanism happening in animals. So more and more have robots being more and more used to understand and contribute to fundamental science, neuroscience and biomechanics. And one aspect we started working on is bring all this together then to assist a person who has lost locomotion skills. And there, especially in the field of exoskeletons, there's a wonderful combination of work to be done between people from neuroscience, from biomechanics, and from robotics to create assistive devices, exoskeletons that can assist and support locomotion. And there, some very exciting things are happening in different fields. We started a bit in my lab, but there I think many things can happen in prosthetics and neuroprosthetics.
Mm-hmm. And about the assistive technology, do you think we will get at one point full synchronization with human body? Because I think right now it's either the signals from the brain or the signals from the muscles.
Yeah, there's still lots of work to be done. And here it really depends on the patient or the pilot. So depending if the pilot is a spinal cord injured person with a full spinal cord lesion that has really no control at all, that person requires quite a different assistance. That person really needs like a wheelchair on legs, so a legged wheelchair, because they're and then ideally some kind of natural interface that without thinking too much he or she can control this external device. Then if a person is only partially handicapped, so either only a partial spinal cord lesion or a stroke patient which has maybe hemiplegia where one side of the body is paralyzed but not the other, or possibly some person with a muscle weakness, that really requires person-specific controllers. And that's very challenging because every person is then different, and you want to assist and not make life more difficult, so you really have to guess properly what is the intention of the person, and that's a very big challenge because you want to be safe, you want to be very reactive, you don't want to slow down the person, and you have to be specific, and there's still a lot of work to be done to see how to properly interface. As you said, one way of interfacing is taking EMG signals, muscle signals, and try to augment them. Others might be to measure interaction forces very rapidly and try to augment the person. So if the person moves in one way, measure interaction force and try to follow smoothly the person. Or there could be other interfaces, like maybe EEG, like surface electrodes measuring brain activity, or maybe invasive electrodes to try to guess the motor commands. What are the high level motor commands? And this is a big field of research. How to understand this? You need good progress in the hardware, on the software side. There are many things still to be done in these topics.
I think there's a challenge here in Switzerland called Cybathlon. Is your group taking part in that in any way?
So I'm hosting a group by Dr. Mohamed Bouri, who is making an exoskeleton and preparing for the Cybathlon. They are in very good stages to do one of the Cybathlon competitions. So Cybathlon is a wonderful competition. They do many, I think 6 or 7 competitions in parallel, and on different topics. The one Mohamed Bouri will participate to will be the exoskeleton for spinal cord injured pilots. And that is a wonderful competition because, like, for the first time you start to have benchmarks that are really the same for all the teams. So people they get a score by how well the pilot can cross a terrain with different steps. Like the beginning is already quite difficult, is standing up from a soft sofa chair, and then zigzagging through a terrain, and then climbing stairs, going downstairs, opening a door. And you have to do all this in a sequence, and you get a score by how fast you are. And you get a penalty if some of these key steps you cannot perform. So this is a wonderful way of having a quantification, a score, a quantitative score of how well the pilot is doing. And this is the first time where you can then compare different technologies, different ways of doing, and have a way of people exercising for the same benchmark. So this is a very beautiful competition, yes.
And switching a bit of focus, one of the projects I've seen on your website is called Robotics. Can you tell us a bit more about this project, how it was conceived?
Yeah, so Roombots is what I call a bit my science fiction project. In a sense, it's the idea of Roombots is to use self-reconfigurable modular robots. So think about Lego, the Lego of robotics, little modules that are made of different parts, and on top of that they can actively attach and detach to each other to change morphology over time. So the concept of Roombots came by the fact that up to now all our robots, they were always modular. So quite rapidly we can add limbs, remove limbs, add a tail or remove a tail. But here I had a colleague, Pierre Dillambourg from EPFL, who at some point approached me because there was some option of funding to create adaptive furniture. So, and then we sat together and said, why not use this concept of modular robotics and self-reconfigurable robotics? And other teams in the world, especially in Japan, have worked on that. And then we said, why not bring this concept of self-reconfigurable robotics to furniture to assist someone, for instance, a person in a wheelchair. And here, so we developed modules that can connect to each other, so they can reconfigure. So from a computer, we can program them to attach to each other to get different shapes. And at the same time, we can plug them into existing furniture. So if we attach the attachment mechanism to existing furniture, we can then plug in and connect to it. And I like this idea of adding then functionalities to furniture around a person. Because if you think about, let's say, someone in a wheelchair at home in a small apartment, it could be very useful to give mobility to all the furniture, so that if the person has to cross the room, it could be interesting that the furniture goes away until the person has crossed the room, and then the furniture takes back its original place. Or let's say if you have lost a remote control and it's fallen on the ground, why not have the table go down, pick it up, and bring it to you, as opposed to have I don't know, a human robot doing this. So I think there's a whole opportunity to add functionalities and make the whole environment assistive by having like these robotic modules in the environment. So it's a bit science fiction, but I really feel there's something to make like this ubiquitous robotics assistive for someone. And so we developed some prototypes to explore this. And even beyond furniture, this dream of self-recoverable robotics can be very interesting for multiple applications. If you think about a space station or Mars or a remote terrain, a place that you cannot reach physically by a human, why not basically have a system that you can remotely control, reconfigure, and to change shape and functionality over time, like a satellite reorganizing itself or things like that. So I feel there's a whole field where this self-reconfiguration can be a big bonus. Possibly also a reconfigurable factory line. If you need something where you need to make small productions and you want your factory line to change every day or every week, being self-reconfigurable could be a nice property. And marginally, my dream is to make this hardware, these devices, and share them with the community. And then, like Lego, I think everybody's impressed what people find out and can do with Lego. I think if you give this to anyone, designers or any hobbyist, my dream is to see, give building blocks that can do, where people really do crazy things and beautiful things with them. So that would be a long-term dream.
Yeah. So would you consider open sourcing the project?
Yes, that would be perfect to open sources. In fact, many things we have done are already open source, so people can easily replicate sub parts of it. And I like the spirit of open source. That really helps a lot robotics, so that people can replicate things and improve them.
Is there anything that you found personally useful in open source robotics?
Yeah, well, these days there are many things happening around ROS, the Robotics Operating System. So this is open source, and many libraries for machine vision for things are now developed open source and can be shared, and that's very useful that you can like in robotics, there's not a single team that will have all the expertise needed to do, I don't know, locomotion control, navigation, mechanics, mechatronics. So you always need to collaborate. So being open source is very important. Also, many simulators now are open source. So we use a lot WebBots developed by Robotics, who it's a company that recently made WebBots open source. And that's great for us to share how many of our robots have a simulated model. And so it's easy to share simulation on real hardware, of course. Yeah, so open source is very important for robotics.
And so, since you mentioned ROS, I assume some of your robots use ROS actively?
Yeah, we started doing that. To be honest, so far, many do not do it because just for locomotion and sometimes programming things on very simple microcontrollers, not even having an operating system, just being low computational power, we did many things without so far. Okay. But now, in some of our projects where we adapt our Salamander robots for search and rescue, in collaboration with other Swiss colleagues within something that's called the NCCR in Robotics, National Center of Competence in Robotics. This is really shared work among many teams in Switzerland, and there one of our goals is to have like a fleet of robots, both flying and ground robots, that update maps dynamically. Like all the perception is shared in a common map that's updated by different points of view. And there, ROS is a good tool to share. Like I'm not at all an expert in machine vision, but now being compatible with ROS really allows to collaborate and have a common framework. So for anything that relies on more navigation, vision, all that, things where we don't have the expertise, ROS is very, very interesting.
Well, that's interesting. Yeah. And coming back to those robots, what would you say is the current development level? How far are you from the finished product?
Yeah, that's a good question. So first of all, we have prototypes that are completely house developed, and that's really a challenge. It makes it very expensive, so very time consuming to make and to develop. So we managed to have 12 modules, functional modules. Each of them has 3 motors, so in total is 36 motors. It allows to do many things, but still, it took a long time to get there and do all the mechatronics and everything. So, and they're still a bit fragile. Not that fragile, but still, for instance, they lack a bit of sensing. The reconfiguration planning often needs a bit of human intervention because just the locking is not completely aligned and we need to help it a bit. Now, here is then a challenge for being an academic lab. At some point you need to make it really a product or go beyond this kind of prototypes in labs is you need much more manpower and money. And this is not something that we can do and we don't have the money to do. So here, ideally, at some point, you like to have a startup that manages to collect funds and does all the engineering to make it very sturdy, cheap, easy to produce. And that's something where academia or a lab like me, we are not the best suited to do that. That's something people sometimes forget. But at the university, we have to publish papers, we have to push the state of the art and innovate all the time and do things that no one else has done. Otherwise, our PhD students cannot get a thesis.
Yeah.
And these constraints are quite different from making a product, because making a product means iterating many things to make things easy to produce, more robust and everything. Really important engineering, but a bit more traditional engineering, and clearly not something you can publish. You will never publish a paper on making a thing fault-free for 10,000 hours, because it's very classical engineering. Still very important, but so and that's always a challenge for academia. You will not be able to do this, and not even to be able to compete. For instance, I think Boston Dynamics is doing amazingly well because they have very clever brains, but also many technicians that maintain the hardware and push the limits of good, very solid hardware. That's much harder to do in academia.
Yeah, it makes perfect sense.
Yeah.
And about your lab, how many researchers do you currently have?
So I think we are now more or less 8 PhD students and 4 or 5 postdocs.
Okay.
It always kind of varies a bit depending on the amount of funding we get. Yeah.
And their profile, is it mostly robotics or mixed? Some of them focusing on mechanics, maybe, or?
Yeah. No. That's a good question. So the background is quite diverse. Some is more mechanical engineering, and 2 aspects of mechanical engineers. Some being more control or more really into mechanical design. Some people have more an EE background, electrical engineering for the electronics parts. Some have more computer science background for all the software and the programming. Some are more biomedical, because we have many projects more into the biomedical aspects. And sometimes we have had physicists as well, more for the fundamental neural network models. So it depends a bit on the project, and that's, I would say, the strengths of my lab is it's really the teamwork where everyone benefits from the expertise of others that helps everyone, and you need it to make good progress.
I think I don't have any more questions written, but maybe is there anything that you would like to share, or something that you find really interesting in your field?
Yeah, maybe a few thoughts. Well, first of all, the more I work in robotics, the more I'm really impressed by animals. So you become very humble. by trying to replicate, understand and replicate, you realize we know little, and what we know is not sufficient yet to replicate, and seeing an animal move around, jump, plan complex movements, react very rapidly, do all kind of agility, you realize nature is really amazing, very beautiful. And we're still far from understanding it and replicating it. And even when you think about it, the animal kingdom has many more constraints than our robots. Like, animals have to grow. Mm-hmm. They have to start from a few cells and become a whole adult. So this whole process of development is amazing. The whole process of healing and adapting to changing body shapes, I'm super impressed. Like when you see on YouTube all the videos of an amputee animal, it's amazing how animals rapidly find new gaits or new moving around. So there are many things where both in terms of fundamental science, understanding it, and replicating and bringing it to robotics, I think we still have a lot of work to do. And it's very exciting work at the same time because it's very interdisciplinary. So that's one thing I love, and I'm humbled and fascinated by the animal kingdom. And maybe one more thought is I like the idea of using robots for good. So obviously there's a whole scare of robots either taking over jobs, mm-hmm. or military robots taking over the world. I'm not too worried by each of these, but I think we as a society we have still to think about it and think carefully about it. And I'm personally, for instance, really happy that I don't do any military research. I really want to do only civilian research. But here, in fact, I'm more worried about robots for military application than robot taking over jobs. Mm-hmm. I think robot taking over jobs, I think the society will adapt and find new jobs, human jobs, or interaction like cobots and do better things together rather than the humans disappearing and not being useful anymore. Humans will always stay more creative and can do things better than robots. So the two together will be more useful, and we will have to adapt, but I don't think it will remove too many jobs. One thing that worries a bit more is maybe military application robotics. There I think we have to be careful. There I feel like indeed an army that manages to have better technology, better robots, will risk to more easily start a war. Like once a war becomes a video game because everything is done remotely and you have the robots doing the killing for you, all the military things for you. There, I think, from a society point of view, I think it becomes very risky. So there, I think we have to be very careful what we do and really put limits. Otherwise, that can go in really wrong directions. I think already now with the technology development for advanced countries, war becomes a video game, and that's really a bad thing because then you start wars much more easily. So there, I think we have to be careful as a society and put limits of what's acceptable. But just to finish on a more positive note, mm-hmm. I love robotics. I think robots can do many good things for society. And maybe one message is not only in applications, but also in fundamental science. So something that we forget is a robot can be a very good tool to understand who we are, where we're going, where we came from, this paleontology. And I see more and more use of robots as scientific tools, and that will be very exciting.
Okay, great. So thank you very much for having me in your office here. And well, we'll be following your work on Weekly Robotics. So if there is anything exciting coming up, I'm sure we'll cover it.
Great. Yeah. Thanks a lot for your interest. Yeah.
Thanks.